Welcome to Vica. Founded in 1946 as a family-run business, today the Vica group of companies is a worldwide leader in pressure and temperature measurement. Vica also sets standards in the measurement of level and flow and in calibration technology. Care and precision have always been our policy. So, for us, it is never enough simply to meet the standards. Customers the world over rely on our products and benefit from our broad portfolio of high-precision instruments. We are represented in many countries and can therefore react quickly and competently to customers' needs. Nothing is more important to us than reliability. Our global quality strategy sits right at our core. We have a tradition of the highest standards in quality, and we attach great importance to this. Lean management and a high level of in-house production guarantee an efficiency that benefits both our employees and our customers. We are focused on the details. Our measuring instruments must withstand extreme conditions and operate perfectly in all applications. Only when a Vica product is absolutely safe, robust, and resilient have we achieved our goal. Our customer success is our success. Vica products are the eyes and ears of technical systems and thus an important component of process optimization. Although our instruments may sometimes be small, they carry an enormous responsibility. Our instruments, of course, have the necessary approvals and certifications for worldwide use. Our accredited calibration laboratories provide us and our customers with the most accurate data and offer reliable control. Vica reference instruments are regarded as pioneering. Our worldwide service is designed to meet local needs while also meeting all international norms and standards. Decades of experience serve as the foundation of our technological know-how. From standard products to application-specific developments, we will find the optimal solution for all your requirements. We make our experience and expertise available to serve our customers and work hand in hand for their success. We believe we can still go a bit further and are tirelessly working to improve our products and our services.
Life without pressure gauges would be pretty rough. Figuring out everyday things like oil pressure, air pressure, and blood pressure would be almost impossible. Without pressure gauges, we'd even have trouble taking a proper shower because getting the correct water pressure in our homes would be a hit-and-miss affair. For a pressure gauge to be trustworthy, whether it's measuring gases or liquids, it must be exceptionally well made and accurate. To start, a worker loads an aluminum faceplate into a printing press. It applies a colored scale used for measuring pressure in pounds per square inch. The type of scale it prints depends on the measuring unit being used. Then a worker puts a copper tube into a bending machine that bends, cuts, and flattens sections of the tube. The amount of flattening and bending determines the pressure range the gauge can measure. Each piece becomes a pressure-sensing tube known as a bourdon tube. Then a worker cuts lengths of brass that he machines into connectors. They will link the bourdon tube to an inlet pipe. He melts zinc solder in the connector's receptacle, and he mounts the bourdon tube in the correct position. He fills the gap between the connector and the bourdon tube with solder. Then he flushes the heated piece with water to cool it down, sealing the tube in place. He puts the cooled piece on a mounting fixture and solders the other end of the bourdon tube to the gauge's internal mechanism. He seals the gap and cools it down. Then he puts the finished pieces, or pressure system assemblies as they are now called, into a cleaning machine. Its hot soapy water washes away any dirt and loose solder particles. The pressure system assemblies then go onto a leak testing machine that pushes air into the tubes. A stable pressure reading indicates there is no leakage. Another worker takes a gear mechanism which controls the mechanical movement inside the gauge and places it on the connector. A machine screws the gear mechanism in place. He then takes the gear's connecting link and rivets it to the pressure system assembly. He fits the pressure system assembly inside a protective stainless steel housing. A machine screws it all together. Next, a worker calibrates the assembly. She loosens up the connecting links slightly to prevent friction, puts on the indicator needle, and runs a test. After a bit more adjusting, she puts the faceplate and the indicator needle back on. She ensures the gauge reads accurately at 3 key positions, and then screws the faceplate onto the gauge. A final test confirms it is calibrated properly. Then she puts a glass cover over the faceplate and adds a steel ring to hold it in place. A crimping machine evenly folds the ring's edge until it makes a perfect seal. Now she fills the gauge with glycerin. Glycerin lubricates the internal mechanical parts and increases the lifetime of the gauge. Glycerin also absorbs vibration well, which helps the indicator needle remain stable during operation. A worker completes the pressure gauge by sealing off the fill hole with a rubber plug. But of course, not all gauges are built the same way. As accurate and dependable as a Swiss watch, a trustworthy pressure gauge also has a pretty face.
world of temperature gauging, the dial thermometer is a lot easier to read than a glass stem thermometer. A needle points to bold numbers on a dial, and even from a distance, it only takes a quick glance to confirm an initial impression that things are heating up. All the highs and lows are plain to see on the face of a dial thermometer. It often comes with lengthy tubing to measure temperature from afar. It's a handy feature for power plants and heating and refrigeration systems. To begin, rollers straighten very narrow metal tubing. Then a blade cuts it to length, depending on the application. As the blade makes the cut, a mechanism pries open the ends. Next, a worker inserts a fitting into a much wider tube that will become the thermometer sensor bulb. He secures the tube in a fixture and welds the narrow tubing machined earlier to the fitting on the end of the bulb. With the bulb and tubing now linked, production moves to the next stage, the making of the burden tube, which is a kind of spring. A worker cuts flat, wafer-thin tubing to length. Down the line, they clamp the flat tubes in a device that's on a track. It moves past an arc welder that melts and closes one end of the flat tubes. Here's a before and after comparison. A worker now encloses the tube in a die and drives a pin into its open end. This widens and redefines the opening from inside and outside. He slides it over another pin and activates a mechanical punch press. This fine-tunes the shape and dimensions of the opening. The next worker clamps the tube in another device. He operates a roller to wrap it around a mandrel, bending it into a C shape. This completes the thermometer's burden tube spring. The next worker clamps a bracket to the bottom of the burden tube. He inserts a small piece of connector tubing in the burden tube hole and applies liberal amounts of a flux compound. The flux prevents tarnishing of the metal as he melts silver solder to braze the parts together and to seal the opening. Now a test. He pumps gas into several burden tubes and immerses them in water. If no gas bubbles out of the tubes, it means the tubes are perfectly sealed. The gas pressure also causes the tubes to spring into action. It's this action that will move the pointer on the dial of the thermometer. The next worker attaches a brass connector to the tubing. He brazes them together to create a solid bond. He folds the brazed parts into the curve of the burden tube and pushes it into place with a mechanical press. He installs the gear assembly that will translate the linear movement of the burden tube into the rotational movement of the thermometer pointer. He screws the dual temperature dial to the burden tube assembly. The more detailed and extensive the scale, the bigger the dial. This one is mid-sized. And now everything comes together as he tethers the sensing bulb along with a short fill tube to the back of the burden tube assembly. Using a brazing torch and solder, he seals the connection. He then steam cleans the brazed joint. He buries the bulb in a hot sand bath, which causes any moisture in it to evaporate. Through the fill tube, he fills the bulb with nitrogen gas. To calibrate the thermometer, he plunges the sensing bulb into boiling water and adjusts the pressure of the nitrogen gas until the dial reads 100 degrees Celsius. The fill tube's job is now done, so he crimps it to seal it off. He tests its accuracy by immersing the sensing bulb in numerous controlled baths, each one a different temperature. And if it's on the mark, he encloses the inner workings in the stainless steel case. He protects the joint with a special metal spring and snaps a clear window to the case. A gasket between them ensures a dust-proof seal. He screws a part called a well to the sensing bulb connector. The well will protect it in high-pressure situations. This dial thermometer is now ready for the ups and downs of temperature gauging.
Pressure sensors are available in various designs and variants and have proven themselves in multiple industrial applications, even under difficult conditions. Let's take a quick look at the design and function of a pressure sensor. The pressure sensor is screwed into the measuring point at the process connection. The pressure sensor element converts the present pressure into an electrical signal. The downstream electronics amplifies and standardizes this signal. A suitable case protects against environmental influences. The standardized signal is transmitted to the following signal evaluation via the electrical connection. Now we see how individual components are assembled in the production. In the first step, the process connection is welded to the pressure sensor element. In the application, the pressure sensor is screwed into the measuring point via the process connection. The pressure sensor element converts the present pressure into an electrical signal. After that, the PCB is mounted. The electronics amplifies and standardizes the sensor signal. Now, only the necessary electrical connection between sensor and PCB is missing. The assembly is being auto-frettaged. A pressure above the respective overload range is applied to the pressure sensor to ensure a long-term pressure stability. In the next step, the case is mounted. It protects the electronics against mechanical and environmental influences. To improve the legibility and durability of the product label, the pressure sensors are labeled with a laser. This is done in one working step with the welding of the case. The electrical connection is installed. In the application, it is used to transmit the standardized signal to the following signal evaluation. During pressure adjustment, the accuracy of the characteristic curve is determined and the pressure sensor is adjusted accordingly. Simultaneously, a high voltage test, including functional check, is carried out. The finished instrument is packed together with accessories. The instrument documentation, such as operating instructions and test report, is enclosed. Finally, the packaging label is affixed. The pressure sensor is now ready for dispatch.